Okay, let's continue. In the last class, we looked at what are the possible things that can go wrong in the pipeline ADC. So we basically, where was it? Yeah, we basically started by looking at what can go wrong if we have some issues in the ADC, and we saw any issue in the ADC can be thought of as having an error in the flash reference voltages. And when we had an error in those reference voltages, we saw that if we use a maximum gain times the quantization noise can exceed the range for the succeeding stage. So what was the solution for this? We decided to use a smaller gain, and it's slightly bit more convenient to use gains in the power of 2. So we decided to use a gain which is 1/2 the maximum gain. And when you do that, now the addition is no longer a trivial concatenation. You actually have to go and do this addition. And this is what we called as redundancy, and we call this to be 1-bit redundancy because gain is basically half the maximum gain, right? And then we went on to see that we know that if we make an error, where is it? Yeah, in each of these reference voltages, with the redundancy, that is a smaller gain, we are okay. So we saw what is the maximum tolerable error, and that was basically plus or minus Vref by 4 for a 2-bit case. And in general, you can show that if you have a gain which is half the maximum gain, the tolerable error is plus or minus delta by 2. So the thought process was the following: I know this can be errored this much, this can be errored this much. So we decided to make an error in these two, so that merges into one level like this. So which means instead of having to use 3 comparators, we only have to use 2 comparators, and that's a good saving in a flash ADC, right? And this gave rise to the 1.5 bit stage, and you can basically extend it to any m plus 0.5 bit stage. And then we saw how to realize this DAC and this amplifier in one shot, and that basically gave rise to this structure. See, multiplying DAC. So essentially, maybe if I copy this, yeah, maybe let me have it here. Yeah, so here we basically, for a 2-bit case, we have 4 switch capacitor branches, each with a capacitance of C1 by 4, and we have 3 thermometric bits, and these 3 branches control the thermometric bits. Now with respect to the inputs, if you see, each branch samples a voltage and acquires a charge of Y times C1 by 4. So the charge transferred from each branch is C1 by 4 times Y, and you have 4 branches transferring this charge. So this charge by C2 gives the output voltage. Now similarly, with respect to the thermometric bits, you see that if this bit is 1, you transfer a charge of Vref times C1 by 4 with a negative polarity. So I can write it as C1 by 4 times Vref times V1A. That will be the charge transferred from the first branch. Similarly, you can write it for the second branches like this, and for the third branch, the charge transferred is this, and divided by C2 is the final output, and this way you get the required input minus DAC, right? And we saw what can go wrong here. Here one issue was the fact that the capacitors used in the DAC, they can be mismatched, and we essentially saw that if the capacitors have mismatch, yeah, the DAC characteristic will be completely nonlinear. So at the output, you will have increased quantization noise floor as well as input harmonics, right? And we saw in principle you can correct it using digital calibration. And again, the basic idea is this. If I have this, yeah. So this is the ideal output if the capacitors are all matched. So let me write it here. Push it here. So this is the ideal output you get from the DAC. So this I can write it as basically C1 by C2 times Y minus C1 by 4 into Vref into, or I'll write it like this, Vref by 4 into C1 into V1A plus C1 into V1B plus C1 into V1C. I've just rewritten the same thing, taking only Vref and 4C2 outside here, right? Now this is what will happen if the capacitors are matched. Now if the capacitors are mismatched, that is, this capacitor is some C1 by 4 plus delta C1, this is some C1 by 4 plus delta C2, this is C1 by 4 plus delta C3. So what will happen to this voltage? I mean, from here, what will happen? If I rewrite this, what will happen? Let's say with respect to the input, there is no issues, only for the DAC you tell me. I mean, this you are going to rewrite it. If I take out Vref by, let us say, 4C2, what all I'll have here? C1 plus 4 delta C1, okay, times B1A plus C1 plus 4 delta C2 times B1B, C1 plus 4 delta C3 into V1C. Right? I mean, if you write it, if I take C1 also out from here, then it's basically 1 plus delta C1 by C1 by 4, right? Plus we have the same thing. So this will be the actual signal you get from the DAC, right? So if you look at the, let us say, two-stage pipeline, you have the input going to the first ADC, and you have the DAC here. So you take the difference and multiply with some gain, give it to the second ADC. Now how will you reconstruct the final output? V1 plus V2 by the gain, okay, and let's call this as the DAC output. So with the capacitor mismatch, this is the DAC output, right? Let's call this some V hat. I write it here. So this is the DAC output. Let us say call it V hat. This is the signal Y. What will be the signal here? If this is a signal Y, this is V hat, what will be the signal here? So what will be the input to the second ADC? So if the second ADC adds a quantization noise Q2, what is V2? V hat plus Q2, right? So now if you basically rewrite this, I'll have V1 plus this entire term by G. So what will come if you divide this by G? We have Y minus V hat. In this, what is the desired term at the output? Ideally, what you want this output to be? You want the input to appear and the last stage quantization noise. So which means the way I have to take this, I have to make sure V1 is same as V hat, right? That means the following. Remember, this is, we have assumed to be a 2-bit flash. So we have 3 thermometric bits, V1A, V1B, V1C. So from these bits, you reconstruct V1 in this fashion. Right? So if I have to finish it, that is plus 1 plus say delta C2 by C1 by 4 into V1B plus whatever 1 plus something into V1C. So instead of taking the final output as sum of the 3 thermometric bits, which is what you typically will do, you basically have to scale them appropriately and then take that as your final output V1. If you do that, this term gets cancelled, and that's how we can digitally calibrate. Cool. Yeah, and also the last class we also saw what happens if the gain we have is not exactly the value you want, right? So ideally you want this gain to be equal to some G, but in practice this analog gain cannot be exactly made to the value you want. So if I do that, if there is a mismatch in the analog and the digital gain, then along with the required term, even the quantization noise from the previous stage that doesn't completely get cancelled, you have a portion of it up here. So that will result in increased noise floor. And how did we decide to correct for this? You basically have to make these two to be equal. So we can basically change this or this. Which one do you prefer? The digital gain, because they're just changing multiplication factor, right? So that's what you do. You do digital calibration to correct for it. Okay. So we'll continue this discussion. So we have seen all major non-idealities. So now let's look at another non-ideality, and this is something you can't really do anything about. And what non-ideality is that? Thermal noise. So that's what we'll see. Maybe I can copy this. Let's see. Let me erase all the unnecessary stuff. So here, which all blocks can add noise? And first of all, let me redraw this. This entire thing we implemented as an MDAC, right? This DAC and the subtraction was realized as one single circuit. Let me redraw that maybe. So this is basically MDAC 1. Let us say this has a gain of G1, and this is basically given out like this. And let's also draw one more stage. Let us say the second stage also is given to another MDAC. This has a gain of G2, and then you have the third ADC like this. So here, first of all, how will you reconstruct the final output from V1, V2, V3? V1 plus V2 by G1, V3 by G1, G2. Now let us say the quantization noise added by the first ADC. So let me draw it internally like this. So let us say this is adding a quantization noise Q1. This is adding Q2 and Q3. At the output, what will be the final quantization noise I'll have? Only the quantization noise from the last stage, and that will be divided by the entire gain preceding this. So I'll have the input plus the last stage quantization noise divided by the overall gain. So this much we know already. So now let's see what all blocks can add thermal noise. So which all blocks can add thermal noise here? I mean, so tell me which all blocks can add noise here? ADC can add noise, and these are the two things, and both of them add noise. See, remember, anytime you make something with a transistor or resistor, there will be noise. That's all. Something you can't escape from. So let's first see what happens due to the noise from the ADC. Okay. So if the ADC is adding thermal noise, I can model it like this. Along with the quantization noise, it is as though I am adding some thermal noise. Let us say some, I don't know, Px1. Right. Similarly, this is also adding a noise Px2. This is adding a noise Vx3. Now let's look at only the contribution from the first ADC. So how do you think this thermal noise will appear at the output, or what will be the effect of this at the final output? From whatever you know from this, can you tell me what will happen? Why are you saying that it will? So what are the answers we have? You are saying it will add directly. Okay, or what is the possibility? It is adding along with the quantization noise. So how is it going to appear at the output? Why? Yeah, I mean, what he's saying is the simplest thing. I know that if you have quantization noise here, does it appear at the output? So if you add anything along with the quantization noise, will it appear? It's the same point that this is getting added. So anything you add along with the quantization noise, that's not going to appear at the output. So nothing from the first ADC will come. What about the second ADC? So noise from what ADC will be there? And how much will that appear? Vx3? Same thing that happens with the quantization noise for the last stage is what will come here. That's all. So which means thermal noise of the ADC is not critical, because only the last stage thermal noise comes, and if you have sufficient gain before, that's basically a no deal. Cool. So then we are only left with the noise from the MDAC. And for that, let's actually look at the circuit implementation of MDAC so that we get an idea as to how much noise it is adding. So wherever I had the circuit, yeah. So let me take this 2-bit case itself as an example, and let's quickly see how the noise is going to look like. So again, this is same old switch capacitor circuit. You can analyze noise the same way we have been doing. You first consider the noise sources in one clock phase, see the effect of those noise sources at the final output, then take the noise from the noise sources from the second clock phase, find how much is the mean squared noise, and add the two noise powers, right? So now in the first clock phase we have the switches here. So what will be the noise sampled across the capacitor? Yeah, so if I look at the mean squared noise, that's basically KT by, right? That's what 4 KT by C1. So if I look at the charge, mean squared charge stored in the capacitor, how much will that be? Four KT C1 or KT C1 by 4? I mean, remember that this is if I know the voltage, the charge is basically this times C1 by 4 square, so this will give you KT C1 by 4, right? Now similarly, what can you say about the samples, I mean a noise sampled across these capacitors? They'll all have the same variance, but they're not equal, right? They are completely different quantities, just that their mean squared values are same. And in the second clock phase, what happens to the charge stored in this capacitor? You ground this, let us say, so this goes to C2. So what is the total noise charge transferred to C2? KT C1 by 4 plus? So how much is the total noise? So 4 times this goes. Now also remember, in the first clock phase, C2 was also connected to a switch like this. So what will be the noise put in by those resistors? KT by C2, so the charge is, remember in clock phase phi 1, this capacitor sampled this much noise charge. Similarly, this would have already acquired a noise charge with a variance KT times C2. In the second clock phase, you are transferring the charge Q1 from each branch, so this is the total. So how will you find the total output mean squared noise now? This is the charge stored in C2. Output is basically this entire thing. I'll say this is KT C1 plus KT C2 by C2, right? This will be the total output mean squared noise. So this is only the noise in the clock phase phi 1. Similarly, you consider the noise from clock phase phi 2. So in clock phase phi 2, you have these switches and the OTA. Again, to make life simple, we can ignore the switch resistance and consider only the OTA's noise. So if we ignore the switch in the clock phase phi 2, in phi 2 the circuit will look like this, C1 by 4, and then how many branches I'll have like this? I'll have 4 branches, right? I mean, in clock phase phi 2, you basically short everything, right? You are considering noise, there is no signal, so everything is ground. So this is what you have, and you have C2. So this is effectively one capacitance with a value C1. So this is the plain old circuit that you know. You can find what will be the noise due to the OTA and do it. So that will give you something, and that will also be KT by some C to something. So this is the total noise at the output, right? So let me take it here. Yeah. So this is the total noise at the output, right? We have found it. If I were to model this as an equivalent noise added at the input, what will you do? Or maybe I'll rewrite this. So what I'm saying is, I know at the output of the MDAC, I have found the noise power as so much. I want to model this as though the noise is added only at the input side. So how much will be the signal here? And what is the gain from input to the output? it's some gain G1. So it is V out square by, that's what you do. And I mean, if you work out, you will find that yeah, so here this entire thing you divide by the gain. And what is the gain in this circuit? I have already written C1 by C2. So you divide it by whatever, C1 by C2 whole square, and you'll find that this basically the input referred noise will be proportional to some KT by C1. You'll have KT by C1 everywhere into some factor, and that C1 is the capacitance used. Cool. So if that is clear, let's now quickly calculate. So now I'm looking at the noise from the MDAC. So let me erase these. So I know that now I can model the noise from the first MDAC as some equivalent noise Vn1. Similarly from the second MDAC as some other noise Vn2. So tell me, how will this noise appear at the final output? Can you guess? I mean, this noise is getting added along with the input. So how do you think it will appear at the output?
It will appear same as the input.
So whatever happens to the input will happen for this also. So you basically get Vn1 directly. And if I take this guy and try to refer it back here, how will that be? Vn2. So if I want to include the effect of this by adding some other signal here, that will be Vn2 by C1. Fine. So I have basically Vn2 by, so this is, let us say, the effective noise at the input. So if I take the mean squared value, it will just add up because they are all uncorrelated. And I can basically, if I have 3 stages, I'll have Vn3 squared by G1 square, G2 square. Right? And I know noise from each MDAC is proportional to KT by the capacitance used in that stage. So I can rewrite it like this. So I can rewrite it like this. So it is KT by, let us say, CA is the capacitance in the first stage, plus KT by CB, the capacitance used in the second stage, into G1 square. Let us say CC into, this is what you have. So now from, let us say you are given a particular effective number of bits as a specification. From this you can find the signal to noise and distortion ratio you need to have, right? And let us say you are given a particular supply VDD. From here you can find what is the maximum signal power you can provide to the ADC. From these two, what you can find? Yeah, basically it's a sum of noise plus distortion, and you don't want any distortion, so you want this to be almost equal to noise. And we already know this contains both quantization and thermal noise, so you can either have it this way or this way, right? And if you recollect from our calculation for a SAR ADC, for a 10-bit ENOP, the sampling capacitance was just 1 femtofarad, right? And in practice, even the parasitic capacitances might be larger than this. So for lower resolutions like 10 bits, keeping thermal noise smaller is easier, or quantization noise smaller is easier? Thermal noise, keeping it smaller is easier because the capacitance value required from KT by C limit is really small. So it's much easier to actually keep this to be the case. And this is what will happen at low resolution. At low resolution, typically you will find things to be quantization noise limited. Now, if you are looking at very high resolution, say greater than 14-15 bits, then you will find that the capacitance needed will be very large. So there you basically try to keep things to be thermal noise limited, and this is typically a high resolution case. Again, this low high is all a vague statement. So if you want to give some numbers, I'll call, let us say, less than 10 bits as low resolution, and let us say I give you greater than 14 bits as high resolution. Just ballpark numbers, right? And in this case, it will be thermal noise limited. So once, let us say in a pipeline ADC, now you know what is the thermal noise you need to have, and that noise is basically coming only from the MDAC like this, right? So let's see how you might go and distribute this. So let me just do that quickly. I know this is the mean squared noise in the pipeline ADC. I know that this should be equal to some value from my specifications. The question is, how can I distribute it among each stage, right? So of course one choice is to say that I'll have equal noise coming from each stage. Okay, if I say that noise is same, that is this term is equal to this, then if the first stage has a capacitance Ca, what should be the capacitance used in the second stage? These two should be equal, so it is Ca by G1 square. Similarly, you can find the third capacitance will be Cb by G2 square, and so on. If you do this, the noise in each stage is going to be same. So if I had to sketch this as to the stage number versus the noise contribution from the particular stage, how will this look like? It's going to be flat. Each stage is contributing to the same amount of noise, right? But if you do that, which stage has the maximum capacitance? First stage has the maximum capacitance and it reduces. So if I had to sketch the power dissipation as a function of the stage number, which stage will consume the maximum power? First stage, and then it will kind of drop like this. So this is one way in which you can distribute, you can design. You try to keep the noise power same in all the stages, and if you do that, the power consumed in the first stage will be higher and it will continuously drop. So what do you think might be another extreme choice? Yeah, what other choice is this? Instead of keeping the noise power same, you can try to have the same power consumption for each stage, right? So I want to have something like this. The power consumption, I want this to be equal. So which means, what can you say about the capacitances in each stage? If the power consumption is same across stages, the capacitance in the first stage and second stage, how should they be? They should be equal, right? If you use the same capacitance for Ca, Cb, Cc, etc., now which stage is contributing to the maximum noise? First stage, right? So if we again sketch the same plot here, the noise will look like this. So basically these are two extreme cases you can have, and some guy kind of did some long calculations under some approximations. He tried to find what might be a reasonably practical or reasonably optimal choice, and that turns out to lie somewhere in between these two. And can you guess what that choice will be? In one case I am choosing capacitance as C by G square, and the next stage is the previous stage capacitance by the gain square. The other choice is to have all equal capacitances. What might be a middle ground here? That seems they basically try to have a geometric thing, so you can have Ca by G1 as the second stage capacitance. Third stage capacitance can be Cb by G2. This turns out, under a lot of approximate conditions, might be not a bad start. This is not the best optimal solution, but if you want to start, maybe this is a reasonable place to start. Cool. Fine. Cool. So that's what I wanted to talk about pipeline ADC. So again,
Reasonable case for.
if you want to distribute the noise, right? If you want to design, I know what is the total noise power I want. Now the question is, how do I choose the capacitance values, right? I could either have a case where each stage is contributing to the same noise, or each stage is consuming the same amount of power. It turns out you can start with the middle place, wherein, you know, somewhere choose in between, and that is this choice.
Where does this VM3 come?
Uh,
VM3 being the last.
Okay, I took it for a 3-stage. I mean here, let's say I have one more. I generalized it like this. This is for a two-stage. This is for a 3-stage pipeline ADC. If you have a 4-stage pipeline ADC, you will have 3 MDACs. Then you will have. So yeah, bottom line, pipeline ADCs, the resolution only depends on the last stage and the gains you have before it. Okay, and the important thing is to make sure that the signal seen at each of the ADCs here does not exceed the maximum and